This next section of the course is going to deal with trigonometry. We're going to start looking at trigonometry in a new way, both in terms of straight line trigonometry and rotational trigonometry, and what we're going to start with, periodic functions. What's going to be different about it is the way we measure our angles. And we've often or always used degrees to measure angles. And we know in a circle there has to be less than 360 degrees, right, in portion of a circle. What we want to do in this unit is talk about a new way of measuring that angle. And a new way we're going to measure it is in terms of radians. That allows us to use numbers, actual values, as opposed to values with units, which is really what a degree measurement is, right? If I say something is like 75 degrees, it's not a number, it's a number with units. Whereas radians, I tell you something is 2 radians, it doesn't actually have a measurement attached to it. We'd say the word radians just so we know what we're talking about, but 2 is actually just a pure number. The way we measure a radian is by examining the relationship between the central angle, the angle in the center of your circle that you've rotated around, and how far you've rotated that distance in relation to your radius. And so there's three parts to this relationship. Your angle, the distance that's covered by that angle, the arc length, and the measure of your circle. An actual radian, 1 radian, is created as the angle.
Sorry, Josh, come to the main office, please.
When the arc length, this distance here, is exactly equal to the radius. And if those distances are the same, you've created 1 radian, this measurement right here. And we show that by this formula. So your central angle, which is measured in radians, is 1 arc divided by 1 radius, comes out to 1 radian. Now, obviously, your arc length and your radius can change as you make bigger and smaller circles, but as long as that relationship stays the same, that the arc length is the same size as your radius, you have a radian. If your arc length was bigger than your radius, so for instance, my radius was this big, and I swept out all the way to here, so this would be my arc. Well, obviously that distance around is bigger than the radius, so we'd have multiple radians. Maybe it's 2 radians, maybe it's 3 radians. We have to get an understanding of how it's going to work before we can figure that out. And to figure out how that actually works, we're going to go back to the idea of degrees. Because if we understand degrees, we can figure out how radians are going to work. Okay? So degrees, we usually use that to measure straight line trigonometry. If I'm talking about the elevation of a building, great, I'm going to talk about 46 degrees. A radian is used in angular or rotational trigonometry, stuff that goes round and round in circles. To convert from one to the other, which we do sometimes, we examine the simplest circle possible. Think about a circle of radius 1. That's a pretty easy circle to work with. What do I know about this circle in terms of degrees? Well, I know if I started here and went all the way around, that would be 360 degrees. The arc length, when I go all the way around, arc, is actually known as our circumference. So when I measure my arc length, I could think of this as my circumference, which has a measurement of 2 pi r. But for a very simple circle, r is 1. Or in other words, just 2 pi. So I could really say that 360 degrees is equal to 2 pi radians. Or in other words, if I divide both sides by 2, I could say that pi radians equals 180 degrees. And I could use that just a little bit further to say, okay, well, what's 1 radian? Well, 1 radian is equal to 180 over pi, and just divide by both sides by pi, or 1 degree is equal to pi over 180 radians. Okay, so it's actually pretty easy to convert from one to the other. You have these little formulas that come out of this relationship that a pi radian, is equal to 180 degrees. Okay, so there's our summary here. 1 degree is pi over 180. Pi over 180 over pi is 1 radian. It depends on which one you want to convert from or to, which one you're going to use. So let's try some. 60 degrees. I want to convert that to radians. Well, if I know that 1 degree is pi over 180, I can multiply it by 60, and I'll get 60 pi over 180, which reduces to pi over 3 radians. Okay, there's my conversion. 60 degrees is the exact same measurement as pi over 3 radians. Let's try 90 degrees. Same idea. Okay. 90 pi over 180 comes out to what? Pi over 2 radians. Now we don't have to write the word radians in. If we see a pi, we know it means we're talking about radians. That's kind of the big idea there. Not all angles have to be nice ones. So we got 55.23 degrees here. We can still use the same process of pi over 180, which would give us 55.23 pi over 180. And here's where sometimes it doesn't make sense to simplify because we have a decimal and a fraction. We don't really simplify that. But we can think of pi as being a number, right? We know what pi is. Pi is what? 3.1415 dot, 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 dot. So when we do a question like this where we have decimals in a fraction, we usually multiply by pi, the actual value of pi, the number of pi. So 55.23 times pi divided by 180 gives us approximately 0.964 radians. So basically, if you have a decimal question, decimal degrees, you should have a decimal radian. If you have a nice whole number degrees, like 90, 60, you should have a nice fractional radian. Okay, so we can work forwards, we can also work backwards. Let's give it a try. 3 pi over 2. I want to convert that back to degrees. Well, to do that, I have to use the opposite relationship, right? 1 radian is 180 over pi. But I have 3 pi over 2 radians. So I have to multiply by 180 over pi. So on top, we'll get 540 pi over 2 pi. The pi's can cancel because there's one on the top, one on the bottom. And if I divide it out, I get 270 degrees. Okay, just to point out to you something. If you have something bigger than 1, 3 over 2 is bigger than 1, right? We know that 1 pi is 180 degrees. So anything bigger than 1, anything bigger than pi should be more than 180 degrees. That's just a way of checking, am I on the right track? You can try the next one. Negative 5 pi over 3, I want to times by 180 over pi. A little trick for you. You should have a pi on the top and bottom so they can cancel when you want to eliminate it. So if you can't remember which way does the formula go, do I want to put pi's into the question or get pi's out of it? It's really what you want to ask yourself. In this case, I want to get pi's out of it. I'm going to cancel the pi's right off the bat. Okay, we get negative 5 times 180. So that negative 900 over 3. In other words, negative 300 degrees. And you may remember from rotation of trigonometry in grade 11, negative angles means you just go clockwise instead of counterclockwise. Like the decimal degree ones, you could also have decimal radians. I know it's a radian because I don't have a degree symbol. Okay, it's going to be kind of a little trick for us to think about. It has to be radians unless there's a degree symbol for the stuff we're going to deal with. Okay. I want to turn back into degrees. So I got to times it by 180 over pi. Because it was a decimal question, I'm going to have a decimal answer. I'm going to think of pi as that actual number, right? 3.1415 dot, dot, dot. So when I type that into my calculator, it's okay to get decimals. I got 242.93 degrees. Okay, so what kind of problems can we do with this radian degree stuff? Well, the standard set of things we can do with are relating the idea of arc length, radius, and angles to each other. If I'm going round and round in a circle, depends on how big the circle is, how far I've gone around the circle, and I can tell you what angle has been measured. So we can use our formula that the central angle equals our arc length over radius, or you can rearrange it if you want to, as we showed previously. As the arc length can be radius times your central angle. to find out things. Take a look at an example here. Okay, I have a circle with a central angle. That's my central angle right there. Has a radius. I want to know how much of the circle I've gone around. Well, just looking at the diagram, assuming it's to scale, and we can make a judgment on that later. Okay, I know that's less than half the circle, okay, which is less than pi, right? Because pi would be 180 degrees. That would be this much. So it makes sense my central angle is less than pi. It's not a whole pi. But how much of the circle? Well, it depends. Let's take our formula here. If I can use this one, A equals r theta. How much of the circle have we gone around? Well, if the radius is 12 centimeters and our central angle is 2 pi over 3, I can use pi as a pi number or as a decimal, right? I could say, type that in my calculator, I get 12.57 centimeters. That's how far someone has walked around the circle if the person seeing the angle change has an angle of 2 pi over 3. Okay, I can use similar ideas to solve for central angles. We'll just use a different version of the formula. So our angle is our arc length over our radius. What is our arc length here? Well, it tells us it's 32 meters. Okay, our radius, however, is in centimeters. So if I change that to meters, that's 0.14. And if I divide that, we'll get a big number, 229. Just to be a couple more exact, 228.57 radians. And I can put the word rad there if you want to, but we assume it's radians, and that's we're told degrees. Okay, so I can solve for arc length, I can solve for angle, I can solve for other things. Let's take a look at C. I want to know how far the arc length is based on the information that I've been given. So we have that formula for arc length. A equals r theta, which we just had up above. But the challenge in this question, if we take a look at it, is if I solve for the arc length, I'm going to figure out how big this is, because that's what the central angle is measuring. I want a different arc length. I want the opposite side of the circle. So I have to think about, possibly, what is that angle in the middle? Well, that angle in the middle, we'll call it x, is not given to us, but I can solve it if I think about what I know about circles. The central angle for an entire circle would be 2 pi. The angle that we've been given is 3 pi over 5. If I subtract them, I can figure out the opposite side of the circle. What's that? 10 pi over 5 minus 3 pi is what, 7 pi over 5. Knowing that and my radius, I could figure out how big that how big that arc length is. And I get 35.19 radians. Okay, so sometimes you have to think about circles and what you know about them, and we know that all the way around a circle is always 2 pi in terms of angles. A complete circle, because half of a circle, 180 degrees, was a single pi. Okay, some other problems we can solve. Why do I use radians? We often use it, as we said, in rotational trigonometry, and there's lots of things that are turning. In particular, things that rotate, they turn at different velocities, different speeds. Things that spin, for instance, a wheel going round and round, how fast is it going? Well, on straight line, it's going a certain speed, but its wheel itself is spinning at a different speed. The angle going around is measured by the rate at which the central angle changes with respect to time. So what does that mean for us? Well, let's take a look at an example here. We have the hard disk on a personal computer rotating at 7,200 RPMs. That stands for revolutions per minute. It's spinning round and round and round. Our central angle is changing and changing and changing. Right? It's going round and round and round. How fast is it doing that? Well, if I want to find my angular velocity in degrees per second, my velocity. How do I find velocity? Velocity is speed, right? So if I go back to my little triangle, distance, speed, time, that we've talked about so many times before, I can find my speed, my velocity, if I know how far the thing has traveled and the time it took to do that. So how far does this thing travel in the time that we're allowed? If we think about a point on the outside going round and round, that's spinning and spinning and spinning, it's spinning that point 7,200 revolutions per minute. In other words, it's going around a whole circle 7,200 times each minute. So my distance is 360 degrees 7,200 times. That's my distance. My time, and we're talking about per seconds here, if this is revolutions per minute, would be 60 seconds. So I can find my actual speed, the distance I traveled, my distance I traveled divided by my speed, and it turned out to be, we'll put it all together, 43,200 degrees per second. That's how fast this angle in here is changing. Right, that little angle in there. I can do the same thing in radians. I'm just got to measure it in a different way. My velocity, my speed again, I have to think about my distance. How far does this distance travel every second? Well, it's going, again, 7,200 revolutions. What's a revolution in radians? That's 2 pi all the way around the circle. How many times does it do that? 7,200 times in our 60 seconds, which gives us approximately 753.98. This would be radians per second. Okay, very different measurements. I could check it by converting one to the other if I wanted to. I could say, okay, I want to do degrees to radians. Times by pi over 180. It should come out to the same answer. You could check that if you wanted to. And yes, indeed, it does work. Okay, same answer. Okay. But we can analyze this in 2 different ways, right? And get you guys to try one. These ideas of how we can actually use radians to measure something. So the London Eye Ferris wheel has a diameter of 135 and completes 1 revolution in 30 minutes. Can we figure out how fast it's turning the angular velocity in radians per second? So my velocity is my distance over my time. How far is this thing traveling? Okay, what do I know? This is my diameter is 135. What's 135? Which means my radius is half of that, right? It's half of 67.5. Okay. How far is my thing traveling? Okay, well, it goes around the whole circle. Somebody on this thing might start here and go all the way around. They go 2 pi. How many times do they do it? They do 1 revolution in 30 minutes. Ooh, but I want radians per second. So I got to turn minutes into seconds. So 2 pi divided by 1800.00349. Why is that good to know? Well, it's really good to know for what we want to do in part B. I want to know how far the rider traveled at 10 minutes into the ride. So at 10 minutes, well, actually at the beginning, they got on the Ferris wheel, right? Let's pretend it's there. And they've traveled this far in 10 minutes, let's call it. Well, that's my arc length. My arc length, we have a formula for arc length, right? Radius times the central angle. Well, we figured out the radius earlier was 67.5. Our central angle is how much of the circle it's traveled in that 10 minutes. So how far would that be? Well, in 10 minutes, 10 minutes is not a whole revolution because it takes 30 minutes to do a whole revolution. It's 1/3 of a revolution. How much is a revolution? That's 2 pi. So if I plug that all in together, what do I get? I've traveled 141.37 meters. I can problem solve with this. How fast are they traveling? Their angular velocity is this. 0.003 radians per second. I can actually also figure out how far they've traveled. Okay, as a brief introduction to radians, we're going to use them down the road to do more things. Today, what I really want you to be able to figure out is how to convert from radians to degrees, back and forth, and to solve some simple problems involving radius, radians, and arc length. So a couple of little quick questions there. Give them a try. If you're stuck, come see me.